Alright, today we're looking at vector components. I did an introduction to vectors or scalars. That video kind of got us up to where we're at right now. Maybe even went a little bit too far. But how I was describing vectors in that video was already in component form. And so, you remember what components are is they utilize the unit vector. So, the unit vector for the x-axis is called x hat. I call it I hat. You may see it either way. And then the unit vector for the y direction is y hat, or sometimes you'll see j hat. That's what I normally do. And then of course the z direction is z hat or k hat. So if you see I hat, think x hat, j hat, think y hat, and k hat, think z hat. So anyways, the unit vectors, like we said in the last video, they have a magnitude of 1. So they're both of length 1, which means that they contain information to direction. They contain some sort of information as to where they point, but 1 is the multiplicative identity. So when you multiply a vector by a unit vector, you don't actually change it, you just give it a direction, right? So let's look at the components. You remember in the last video I was saying if this is a vector v, we can write it in components. For example, we could say that it's 2 x hat plus 3 y hat, which means that we are, actually let's change this to make it fit the scale a little more. So here's 1 unit vector, 2 unit vector, 3 unit vector, 4 unit vector. It looks like it's about 4 unit vectors, 4 of x hat vectors, right? So we're stacking 4 of them, 1, 2, 3, or 1, 2, 3. It's really more like 3 of them. All right, we'll go with 3. And then in the y direction, well, here's the y unit vector of length 1. How many of those do we stack to get there? Well, there's 1, 2, well, heck, it looks like it's 3 and 3, so we'll stick with that. So we have 3 unit vectors in the x direction, 3 unit vectors in the y direction, and now what we're going to do is we're going to look at another way that we can describe vectors. So directions, you know, I could tell you to walk 1 block this way and turn and walk 1 block this way. And that's one way to give directions, but maybe you want to skip through the park, right? Maybe there's a park there and you can cut through it. And so then, instead of going 1 block this way and 1 block this way, what you might do is you might say, turn 45 degrees in, let's say, the northwardly direction and walk a certain distance, right? Well, the beauty of that, so if we look at the components, right, we stacked up, we decided that if we project this vector onto the x-axis, we end up with 3 x hat vectors of length in the x direction. And if we, let's see here, if we go ahead and do the same and find a component in the y direction, we found there's about 3 y hat vectors. So that's one way to describe a vector. But you may notice that this vector looks a lot like a right triangle, whether you're looking at right here or right here, and that's because it is a right triangle in a sense. And we're going to use the most important right triangle theorem of all time to work with vectors. I mean, it's the most fundamental tool in math, and it is used everywhere. I don't think I've ever had a math class that didn't use Pythagoras' theorem. So what is Pythagoras' theorem about triangles? You probably already know it, so humor me. So if we have this leg, let's say that this is A, leg A, and this is leg B, and this is a leg C, we call this the hypotenuse. Let's put an angle in here. So whichever side is opposite the angle, we call that the opposite. Then we've got the adjacent. Oh geez, I just butchered spelling that. And then the hypotenuse C. Alright, so Pythagorean's equation tells us that if we take the 2 short legs and sum their squares, that equals to the square of the hypotenuse, or the longer leg. And so you may notice here that we decided that the length of this leg was three x hat vector units, 3 units, and then 3 y hat vector units here, so it's 3 and 3. Well, this is kind of like, let's put the angle in here, angle theta. This is kind of like the adjacent side of a right triangle, and this side's kind of like the opposite side of a right triangle. And you'll notice that it transfers over here nicely, and so it's 3 and 3. So we could say that A is 3 squared, plus B is 3 squared, equals C squared. And using that, we can go ahead and take the square root of both sides. Of course, when you introduce a square root, you technically have to put a plus or a minus in front of it from a math perspective. But in this case, we're usually not worried in physics about the negative of the square root. And we'll see other examples of that. So we'll just leave it with the positive one. And of course, 3 squared is 9, plus 3 squared is 9, under the square root equals C. And so that's the square root of 18 equals C. And we can simplify that. We could, 18 is 2 times 9, right? So we could say it's the square root of 2 times the square root of 9. Well, the square root of 9 is 3. So 3 root 2 is our hypotenuse. In this case, it's the length of our true vector. It's actually called the magnitude. So you remember when we talked about vectors, we said there's a magnitude and a direction. Well, the length of the vector is the magnitude. And so if a question asks you for the magnitude of a vector, and all you have are the components, you're going to use Pythagorean theorem in order to find the length of this. So what we've just shown is that this length in this specific vector is length 3 root 2. And now here's another important part, because that's just the magnitude, right? And a vector needs a direction. So the direction in this case is going to be the angle. You know, before it was walk 3 blocks this way, 3 blocks up. Now it's going to be turn some angle and walk 3 root 2 meters or whatever over here. And so in order to do that, we have another tool, our trig functions, sine, cosine, and tangent. In this case, tangent is really useful because remember, before we actually solved for the hypotenuse, the only thing we knew about this right triangle was the adjacent and the opposite lengths. So tangent is a ratio. Tangent of some angle theta is a ratio in a right triangle that has been measured and charted and put in our calculators for us to use. And so tangent is the opposite leg over the adjacent leg. And you'll notice here that the opposite leg for this theta is the y direction, and the adjacent on this leg is in the x direction. So we can write this as y over x. When we're looking to solve for theta, there is a function that undoes a tangent function that's called arctangent. Sometimes you'll see it written as tan minus 1. So arctan theta is equivalent to tan minus 1 theta. Use either one you like. The reason why I use arctan as opposed to tan negative 1/2 is because tan negative 1/2 of theta does not equal 1 over tan of theta. This is something that screwed me up for a while. So if you'll remember, if I have x to the minus 1, I can write it as 1 over x to the 1. That's not true because this minus 1 isn't actually tangent to the minus 1 power. It's indicative of the inverse tangent operator or the arctan operator. And so I'll be using arctan. It's just a lot easier to keep things straight. And so if I take the arctan of both sides here, arctan of both sides, then what I end up with is the arctan and the tan cancel, and we end up with theta equals the arctan of y over x. So how many y unit vectors of length 1 do we have? We have 3 of them, right? So in the y, we're going to put 3 arctan of 3 over, and in the x direction, we also have 3 unit vectors of length 1. So that's the arctan of 1. And I don't have my calculator on me, but if you're going the same direction and distance here, and then going the same distance here in 2 orthogonal directions, you can be assured that the angle is going to be 45 degrees. And so theta in this case is 45 degrees. We use degrees a lot in physics, but there's also times like when we start getting to some angular physics, some angular motion, where we're going to use radians as well. So it's good to get used to this. So if we remember on the unit circle, 45 degrees is pi fourths, because it's half of 90, and 90 is pi halves. So now we have our direction, we have our magnitude. So these two pieces of information, when combined, give us a true vector, right? We've got the magnitude, we've got the direction. In the same way that this was a true vector, it gave us magnitude and a direction, just in a different sort of way. So these are both valid ways. This and that are both valid ways to write a vector. You're going to be doing a lot of converting from one to the other in pretty much probably nearly every problem that you do in this class. So it's good to get comfortable with it. Just remember, when in doubt, Pythagorean theorem is always useful. So I hope this was helpful, and I'll see you next video.